Hello everyone. Welcome to this short talk about bipartite perfect matching as a real polynomial. My name is Gal Benyamini and this is joint work with Noam Nissan. So to begin, let's talk about perfect matchings in bipartite graphs. Say you're given an unweighted balanced bipartite graph. It has n vertices on each side, and you want to determine whether perfect matching exists. That is, a set of edges which is incident to every vertex exactly once. For example, like this, or maybe this. This is a well-studied problem, and we have efficient algorithms, both deterministic and randomized, and streaming and parallel. In our work, we tackle this problem from a different perspective, an algebraic perspective, and we characterize the decision problem and its Boolean dual using multilinear polynomials over the reals. This allows us to deduce upper and lower bounds, and also come across some curious combinatorial oddities, which we'll discuss later. Since our work deals with Boolean functions and polynomials, let's briefly recall the connection between the two. So any Boolean function over n input bits can be uniquely represented by a multilinear polynomial over the reals, where by multilinear we mean that the degree of each variable is at most 1, and by represent we mean that both the function and the polynomial agree on any Boolean input. So for example, the OR function over 3 input bits or the parity function over 2 input bits are represented by these polynomials. For Boolean functions whose inputs correspond to balanced bipartite graphs, we can think of the n-squared input bits as an indicator vector over the edges of the complete bipartite graph. That means that there is a one-to-one correspondence between the n-squared input bits and subgraphs of the complete bipartite graph. So for example, this input graph corresponds to the Boolean vector 1, 0, 1, 1. And if we remove the edge 2, 1, then this graph corresponds to 1, 0, 0, 1. Okay, so we're now ready to present our first result. Consider this Boolean function, BPM, which represents the decision problem of perfect matching. That is, it outputs 1 if and only if the input graph contains a perfect matching of order n. In other words, this is the logical permanent. So our first theorem is a characterization of this function as a multilinear polynomial over the reals. It turns out that the characterization of this polynomial is quite neat. Its monomials correspond exactly to the set of matching covered graphs, and the coefficient of each such monomial is determined by its cyclomatic number, that is, the number of edges minus the number of vertices plus the number of connected components. Our proof of this theorem uses a connection between the Mobius function of the lattice of matching covered graphs and the face lattice of the Birkhoff polytope. However, we remark that we don't know of a simpler proof, even just showing that this polynomial has full total degree, which indeed it does, since the complete bipartite graph is matching covered. Okay, so what exactly are matching covered and elementary graphs? So we say that a balanced bipartite graph is matching covered if and only if it can be written as a not necessarily disjoint union of perfect matchings. In other words, this is equivalent to saying that every edge of the graph participates in some perfect matching. If this graph is also connected, then we say that the graph is elementary. The connected components of matching covered graphs, that is, elementary graphs, were studied at length by Lovász and Plummer, and even earlier by Hetier. To better understand these graphs, let's take a quick look at one such graph. So for example, this graph is composed of 3 perfect matchings, where the colors here simply indicate the matchings, and the graph is a simple graph. However, this graph is not matching covered, since in particular the red edge is not contained in any perfect matching. If we try and take it, we leave 2 isolated vertices. So elementary graphs and matching covered graphs have useful combinatorial characterizations. For example, elementary graphs have a canonical decomposition called the bipartite ear decomposition. We rely heavily on all of these combinatorial characterizations in our proofs. To present our second theorem, let's briefly familiarize ourselves with dual functions. So given any Boolean function, we consider the dual function to be the function in which the bits 0 and 1 switch roles. More formally, we simply negate the input and output bits. We denote the dual of every Boolean function with a star. So for example, the AND function, if we apply the duality transformation, we simply get the OR function. This gives us some intuition. So in the 0-1 basis, that is the original basis, each monomial corresponds to an AND function over the original input bits. Whereas in the dual basis, the 1-0 basis, each monomial corresponds to an OR function over the original input bits. In contrast, in the Fourier basis, each monomial is a parity function. The same duality transformation can also be described as a geometric transformation over the cube. We note that a Boolean function and its dual share several nice properties. For example, their Fourier spectrum is closely related, and also taking the dual of the dual brings us back to the original function. Okay, so to present our second theorem, let's now consider the dual function of the perfect matching function, which we denote by BPM star. By the definition of duality, this is simply the function that returns 1 if and only if the complement of the input graph does not contain a perfect matching. Equivalently, by Hall's marriage theorem, this is the Boolean function which returns 1 if and only if the input graph contains a biclique over a total of n+1 vertices. So our second theorem concerns the characterization of this Boolean function as a multilinear polynomial over the reals. We show two bounds for this function, both an upper and a lower bound. These bounds are expressed in terms of totally ordered graphs. So for the upper bound, we show that any graph that is not totally ordered, its dual coefficient is 0, namely its monomial does not appear. Conversely, for every strictly totally ordered graph, which is a subset of the totally ordered graphs, we have that the dual coefficient is either -1 or 1, and in particular not 0. So these two characterizations, while incomplete, give us a very tight bound on the number of monomials that may appear in BPM star. In particular, the number of monomials is only roughly 2 to the 2n log n. This is in stark contrast to the original polynomial, BPM, which had all the elementary and matching covered graphs as monomials, which are asymptotically almost all graphs, since with high probability a random graph is elementary. We note that the complete characterization of BPM star was originally left as an open problem, but has since been resolved in a follow-up paper. Okay, so what exactly are ordered graphs? We say that a balanced bipartite graph is totally ordered if its left vertices can be arranged such that the neighbor sets form a chain with respect to the subset relation. We also say that the graph is strictly totally ordered if all of these above containments are strict, including the last one. While it might not seem so, these definitions are in fact symmetrical. That is, you could equivalently arrange the right vertices instead. Let's take a look at a quick example. So this graph is strictly totally ordered. Its left vertices are already sorted, and you can see that the neighbor sets indeed form a chain, and all the containments are strict. Whereas this graph is totally ordered, but not strictly so. For example, A3 and A4 have the same neighbors. Observe that this property is not monotone, so for example, adding the edge A4, 4 would yield a graph whose neighbor set no longer forms a chain. From our two theorems, we deduce several corollaries. First, we show the following upper bound. We show that the log of the rank of the communication matrix for the two-party communication problem of perfect matching is bounded only by roughly n log n. By a fully set argument, we can also show a nearly matching lower bound. This is fairly surprising since known algorithms for perfect matching imply a protocol that uses roughly n to the 1.5 communication bits. More on that in a bit. For lower bounds, we consider the following generalized decision trees, whose internal nodes are labeled by ands, ors, and parities. Our result implies that the perfect matching function is evasive even for parity decision trees. This extends the result of Yao, which states that any monotone bipartite graph property is evasive for classical decision trees, where by monotone we mean that the property is not diminished by the addition of edges. Our proof technique for theorem 1 can also be generalized for other monotone graph properties, and implies their evasiveness even over F2. However, while our proof contains topological elements, it is not comparable to the topological approach of Kahn, Sachs, and Sturtevant. For example, their technique does not imply full polynomial degree, whereas ours does, even over F2. For end decision trees, we show optimal hardness up to a constant. And for all decision trees, we only have a quasi-linear lower bound. The same bound also holds for the demand query model, since the queries in that model can be efficiently simulated by ORs. The demand query model is a concrete complexity model for matching that was introduced earlier this year in a SODA paper by Nissan. That model appears to capture the complexity of known combinatorial matching algorithms, and therefore obtaining a polynomially larger lower bound for that model would be very interesting. Finally, we observe some combinatorial curiosities. For example, we deduce a closed form expression counting the number of bipartite graphs with a perfect matching. And we show that this number is always odd. The same also holds for all matching covered graphs. And also, for example, if you take the Fourier transform of BPM, we can show that the Fourier coefficients of all elementary graphs, which are symptotically almost all graphs, is the smallest possible, exactly 2 over 2 to the n squared. Okay, so let's briefly discuss the first corollary in more depth. Consider the following two-party communication problem. First, we fix any arbitrary partition of the complete bipartite graph's edges into two sets. So for example, consider a partition in which we take all the edges incident to some subset of the left vertices, and the other partition is the remaining edges. Now, for every input graph G, each of our two parties, Alice and Bob, receives their share of the graph. Their goal is to communicate the least bits possible and arrive deterministically at the correct answer, that is, whether G has a perfect matching or not. So the communication complexity of this problem is simply the maximum number of bits communicated on the worst case input. Okay, so the known algorithms for perfect matching, such as that of Hopcroft and Karp, imply a communication protocol which uses roughly n to the 1.5 communication bits in the worst case. Our result implies an upper bound, not for the communication complexity, but rather for the rank of the communication matrix. So what is the communication matrix? This is simply a matrix whose rows are indexed by Alice's inputs, columns by Bob's inputs, and the entry is 1 if and only if the graph defined by their joint input contains a perfect matching. So a classical result by Melhorn and Schmidt states that the log of the rank of the communication matrix over the reals lower bounds the communication complexity. This holds for any communication problem. The log rank is also conjectured to be polynomially related to the communication complexity through the famous log rank conjecture. Our sparse characterization of BPM star induces a low rank decomposition of the communication matrix as follows. Simply think of any monomial of this polynomial as a rank 1 matrix. It is the outer product of Alice's input and Bob's input. Let me just say that the exact communication complexity of this problem remains undetermined. So as of yet, we have a nearly tight bound on the rank of the communication matrix, but the only upper bound we know on the communication complexity is n to the 1.5. So closing this gap remains an open question. Finally, let's take a quick bird's eye view at our proof techniques. So let's begin with the characterization of BPM, that is theorem 1. This characterization follows by investigating the lattice of matching covered graphs, with the relation being containment over the edges. So for our first step, we show a relation between the coefficients of BPM and the Mobius numbers corresponding to this lattice of matching covered graphs. The Mobius function is an inductively defined function, which is defined for every poset and is related to its incidence algebra. This function assigns a value to every interval in the lattice and can be seen as a generalization of the Mobius function from number theory. Our second step is to use the characterization by Bilera and Sangarajan, who show that the matching covered lattice is isomorphic to the face lattice of the Birkhoff polytope and is therefore Eulerian. An Eulerian lattice is a lattice in which we have some kind of even-odd condition. That is to say, in every interval, the number of even-ranked elements and the number of odd-ranked elements is the same. Finally, we simply compute the Mobius function of this lattice. So for any Eulerian lattice or any face lattice of a polytope, the Mobius function is uniquely determined by the ranks of the lattice. We show that the ranks of our lattice are given exactly by the cyclomatic numbers, and for this proof we use the bipartite ear decomposition. For theorem 2, things get a bit more complicated. Applying the duality transformation to BPM immediately shows us that the dual coefficient of any graph, not necessarily matching covered, is given by the sum of original coefficients, that is Mobius numbers, in the upper set corresponding to that graph in the matching covered lattice. Had this been a downwards closed interval, it would have immediately followed by the definition of the Mobius function that the sum of Mobius numbers in any downwards closed interval is 0. However, in an Eulerian lattice, because of the even-odd property, the sum of Mobius numbers in any non-trivial closed interval is 0. That means that even for upper sets of this form, we have that the sum of Mobius numbers is 0. Since the upper set of any matching covered graph in the matching covered lattice is an interval, we have that for any such graph, other than the complete bipartite graph, the dual coefficient indeed vanishes. So no matching covered graph appears as a monomial of the dual. While this family constitutes asymptotically almost all graphs, this is far from sufficient for theorem 2. To extend beyond the matching covered lattice, we therefore need to characterize the upper sets of all balanced bipartite graphs, not only those that are matching covered. So for example, this graph, which is not matching covered, its upper set is not an interval. Nevertheless, we show that any graph that is not totally ordered, its upper set nevertheless satisfies an even-odd condition, and therefore its dual coefficient vanishes. Our proof of this fact follows broadly by factorizing the upper set of such graphs. This factorization can be shown to exist for any non-totally ordered graph using arithmetization of the dual, the bipartite ear decomposition, and the combinatorial characterization of elementary graphs due to Etier. The details here are a fair bit more complicated and appear in our paper. So to summarize, in this paper we characterize the bipartite perfect matching function and its Boolean dual using polynomials. These characterizations imply complexity theoretic results, of which we've seen a few. However, many open questions remain. Our first open question was to determine the complete characterization of BPM star, but this has since been resolved in a follow-up paper. The second question regards the communication complexity of bipartite perfect matching. So our work implies a log-rank bound of roughly n log n, and known algorithms imply a communication complexity bound of about n to the 1.5. We remain hopeful that the dual polynomial can be used to construct efficient communication algorithms for this problem using even a quasi-linear number of bits. This is left as an open problem. Conversely, regarding lower bounds, as we've mentioned, we obtain a quasi-linear lower bound for OR decision trees, which also holds for the demand query model. Since that model appears to capture many combinatorial algorithms for perfect matching, it would be very interesting to improve this bound polynomially to something on the order of n to the 1 plus epsilon for some constant epsilon. Let me just remark that our lower bound technique works against all decision trees whose queries are of any arity, whereas to simulate demand queries, we only need all queries of arity n. So perhaps this technique could be refined to improve the bound. Anyway, that's it, and thank you very much for listening.